Hi, Hao.
Hi, Peter. Long time no see. How are you?
I'm fine, and thank you very much because you want to join my podcast on everyday metallurgy.
My pleasure. I've been very exciting to see your previous episode. Very interesting.
Thank you. How you're one of my old friends in this world. We have been traveling together a long time ago to Aachen, where in a car with you for 10 hours each direction was really a joyful experience.
Oh yes,
Uh,
I still remember when I was driving. Then you were sleeping. You fall asleep. I'm pretty sure I did the same. It was a long journey, but that was a very pleasant journey.
yeah. Uh, how you are working with some special materials called thermoelectrics, and they are quite rare. It's not that often people talk about it, and when you say thermoelectric, people just, oh, what is that? What does it mean? So you are, I think, one of the European experts within this material. So therefore, I would like to talk to you and learn more about them and how they are used, where they are from, and so on. But first, will you introduce yourself, your name, what you do, where you work, and your background, and especially how did you find interest in material science?
Absolutely. I'd love to talk about thermoelectrics. And not because I've been dealing with thermoelectrics for my entire research career and working career, also because if you haven't heard about thermoelectrics, then you're not alone. Because these people, including my father, he didn't heard about the thermoelectrics before I introduced this to him. I really think this material deserves more attention. But a few words about me myself. I came to Denmark for pursue my PhD in chemistry in 2008. Then after that, during my PhD research, we got some patents. Um, and then the company which I'm working in called TEGnology is founded based on those patents. And then I joined the company as the first employee responsible for further development of the materials. And now I'm sitting as the manager of the company. So it's really exciting journey for me. So thermoelectric materials, when it's named, it's thermo. Thermo means heat. So this material deals with heat and then electricity. More specifically, if this material sees a temperature difference, means one side cold and one side hot, it will generate a small electrical potential without any moving parts, without chemical reactions, and without, of course, CO2 emission. If you think it's magic, then it's not. It's science.
Yeah.
So my personal motivation of working with materials is because I was told in my high school that people moving from Stone Age to the Iron Stage or the electronic age is not because we're running out of stones or woods, because we have discovered better materials. So materials is really the fundamental of everything. So without a functioning material, it's impossible to imagine everything we're dealing with. Cell phones, computers are based on silicon, solar panels, also based on PV materials, so on and so forth. So material is really the fundamental, and that's fascinated me for all these years, and will be for my entire life.
Yeah. Thank you. Good introduction. Then I would like to dig a little deeper into this. How does they work, these thermoelectric materials? Because you set up a system with something you call cells. Can you explain how they work theoretically?
Absolutely. So thermoelectrics is based on semiconductors. A semiconductor means in these materials we have carriers, so electrons or holes, they can move. Well, this is not the something that you can see moving by your naked eyes. It's just the electrons that moves under a temperature gradients. And this movement, also called diffusion, if you'd like to, diffuse under the driven by the temperature gradients, will form an electrical potential. And that if we put these materials in a certain way, so the electrical potential can build up, and then it can generate a useful power. The phenomenon was first discovered almost 200 years ago. That was the fundament that people found that when they connect two metal, different kind of metals, and then when the junction is heated, there's a magnetic fields generated along the wires. Then people figure out, okay, electricity is generated caused by the temperature difference. That's how thermoelectrics is discovered. And nowadays, there's a good reason you haven't heard about thermoelectrics, because the most successful application is in the space, in the deep space, where it's so far away from the sun that even solar panels cannot harvest enough cannot harvest enough sun to generate enough energy. So then people use radioactive material to generate heat and then convert that heat into electricity. Because as I said, there's no moving parts, so it's so reliable that it will work for decades. The satellites that the NASA has launched has already worked for 40 years and still generating power. So it's very, very reliable. And then in the recent years, people want to utilize that space technology into industry, because we know whatever we do, we will generate some heat. And in many cases, this heat is just wasted in heating up the air around us. And then in the recent years, we have the energy crisis, and also people want to increase the efficiency. Then we think, why don't we reuse the heat by putting thermoelectric harvesters to generate electricity? When heat is free, then even a small amount of electricity will be a pure gain, as long as we can produce those harvesters in a cheap and a scalable way.
What temperature spans and what temperatures are you typically working at?
There are different materials works in different temperature ranges. In our case, in TEGnology, we are mainly looking into low-grade waste heat from industry. That means we're dealing with from room temperature or even a little below to 200 degrees. So because it's not saying that above 200 thermoelectrics won't work. Actually, it will even have higher efficiency at high temperature. But the thing for us is when the temperature is higher, the value of the heat is also higher. So people will not call it waste heat anymore. People might already reuse those heat. But in this low-grade heat below 200, it's really, really difficult to utilize it. Of course, now, especially in Denmark, people talk about sector coupling. So the waste heat from one sector can be used for house heating. But still, we only use a small portion of the excessive heat from industry.
What is typical efficiency of such a system?
In general, thermoelectrics is a low efficient power generation technology. So in the best case, with the best material in the extreme working condition, we might gain above 10% or 10-12%. But usually, because if we have in practice, we usually have a broad temperature range where the specific material only reaches peak performance in a relatively narrow temperature range. So in reality, we see a few percent, 3, 5, 8% efficiency of this material. But again, we want to argue that the good application for thermoelectrics is the application where efficiency doesn't matter that much. It's not to say it doesn't matter at all. It means that the availability of the power exceeds the high efficiency in those applications. For example, in the space, there's no alternative. And we don't need high efficiency, we just need power. And the same in the application that we want to identify is where heat is available. In the better case, that temperature difference is available, so we don't need to actively cool the other side. And then power or electricity is not available at the place. But maybe we can talk more about the specific applications later.
Yeah, let's do that. Because I would like to dig a little deeper into the materials you use to make thermoelectricity. I know historically it was quite rare materials, and maybe they were also a little dangerous to handle. Can you tell about the history of thermoelectric materials, how it has evolved?
This is a really good question that I'd love to elaborate. So the state-of-the-art material right now is based on an element called tellurium. Tellurium is a very rare element. It's rarer than gold on Earth. But still, it was chosen by NASA as their material because they know they're going to use in the deep space, and they're not going to build many of them. So instead, this material is very reliable and high efficiency. So that was the reason it was chosen. But if you want to use this material into the industry, then we see the drawbacks, because the price will be too high. Actually, before we reach the price, we will find out that it's not enough material on Earth to support industrial application. Therefore, there's a huge interest in academia, or both in academia and the industry, to find alternative materials to tellurium-based material. And this is also TEGnology is working with, that we work with tellurium-free material. We only use environmentally friendly and abundant material. This is not to say that the deep space application is not a good application, because that material fits their needs. It's a very good, successful application. But in industry, for us, we also need to find material that meets our needs.
Yeah. So what kind of materials are you looking at? I know your PhD was exactly about these more abundant materials.
Exactly.
Can you disclose a little on that?
Oh, yes. We work with zinc and magnesium and antimony-based materials. That's a different combination of these elements. Then, of course, we also add some other elements to fine-tune the performance of the material. But in general, all the materials like zinc and magnesium, antimony. Antimony is heavy elements. You don't want to eat it, but they are more environmentally friendly. I think I can say that than tellurium.
Yeah.
That also leads to a much lower price of the raw material.
Yeah, quite important.
Absolutely. When it comes to industrial application, it's all about return of investment.
And where do you find these materials? I know there's a project where you participate on European level right now to find raw materials in Europe for this.
Tellurium is only produced in a few countries in the world, including Russia and China, and then Canada is coming after. So it's not a reliable supply of these raw elements. So everyone is looking for a better material with a more sustainable supply. So by joining this European project, this specific one is we're looking at a material called tetrahedrite. It's a special mineral that basically we can dig it out from the mines. And then we also happen to have a lot of mine in Europe. Therefore, it's despite the lower efficiency of this material, it's still very interesting to see if we can build the harvester on these materials.
Yeah, and if we look deeper into the materials, some of the alloys you are creating, they're not really stable. So if you make a phase diagram, they are quite separate in each side of the equilibrium. So how do you handle that and ensure that you get the right mix?
It's difficult.
Yeah, that's a big secret.
So it's not. Well, it's not a secret that it's difficult. Everyone knows it's secret, but that's why we are here. When the material, let me put it this way: there's no perfect material in the world. Any material, they always meet some requirement, but don't meet the other. So of course we want to maximize the advantage and then try to compensate the disadvantage. For example, in our material, it's less stable at high temperature. Well, I guess it applies to generally it applies to any material, but especially we want to stabilize our material by fine-tune the composition and also to play with, for example, the grain size. Eventually, we can also coat the material so to protect it from oxidation or the reaction from at the boundaries at the elevated temperature. So there are many ways of modifying the material to meet our needs. And that's all about material science and engineering.
Yeah, I think that's the amazing part of your work, where if people are listening to this, contact Hao, because this is extremely interesting and it is a fantastic material to work on and process. How let's jump from the materials to applications. I know that you are working on some very specific applications, and I really like the way you think integrating this in Industry 4.0 with sensor and digitalization. Can you tell a little about your product?
Absolutely. So for me, it's in the beginning, I said I was fascinated by what thermoelectrics can do. But when I joined the company, I realized that we need to, for the company to survive, we need to have business. Only fun is not enough to run the company. And we don't think we can persuade NASA to use our product as their next generation of TEGs, thermal generators. Then we have to identify new applications, and that came this industrial, low-grade heat, because it's in such a huge amount, and we think if we can only utilize a small portion of this waste heat, we can have make a difference. Therefore, we really look into identifying the needs. The needs turn out to be that, or when we come into this area, then we suddenly have competitors. We're competing with, in larger scale, we're competing with other renewable energies from PV, from windmill, and for small scales, we're competing with batteries, because there are some applications where we think if we can just generate a small amount of electricity by the process heat or the heat generated by any machine, then we can replace the batteries. Then, of course, we cannot replace all the batteries because batteries are so cheap and so easy to use. Whenever people can use battery, they will still use the battery. And then our thinking is in the places where using battery or changing batteries are difficult. And also those places where there's no sun, so you cannot harvest the sunlight, or there's no movement, but there's a heat. And it's those applications that we really want to identify, and it turns out to be indeed at the background of Industrial 4.0 and digitalization. There's more and more applications that people want to have more reliable power supply instead of batteries to power their sensors, so they can have more data and more reliable communication on their sensors. For example, I can give you an example for example, on the top of a house, on top of the chimney, where you want to measure something. Of course, you can use the battery, but then in those high temperature, high moisture areas, batteries might not last long. And also, every time you want to change the battery, it's not a battery cost. It's the manpower, right?
Yeah,
and also in some places, for example, underground pipelines for district heating or for water supply, apparently there's no light, no power, no grid. And also when you line the pipelines, it's very difficult to dig the street out again to change the battery.
Yeah. So you have been successful at that?
I want to be more successful on that. Let's put it this way.
Okay.
It's still an emerging technology, I must say. So there's a significant lack of awareness what thermoelectrics can do, because many people have tried it and have experienced based on the existing solutions or the existing products, where the products on the market might not really fit their applications. Then they get a bad experience, the bad reputation for thermoelectrics. And that's something that we are up against.
Yeah. So there has been some front runners that has promised too much.
Well, I don't think they're doing it on purpose. It's just that they are they are using the old solution to solve the new challenges. For example, the first thermoelectric generator or components use ceramic substrates because they were supposed to use at 300 degrees. But those ceramic substrates, it's thick and brittle. If you use that in our low temperature applications, it's actually block the heat from reaching the active material. And also in our applications, people want to implement in large scale or large areas, and then using ceramic substrates is the bottleneck. For doing that is will be too expensive. And then we think, okay, can we replace those ceramic substrates? And that leads to a completely new product which is flexible, and people can implement in larger scale.
Good thinking. How, if people want to learn more about thermoelectrics, where should they head?
Well, we would definitely be happy to talk to people who is interested in knowing more about it. But then I would say, think about where there's a heat. There's a possibility that we can generate some electrical power. It depends on, of course, on the temperature, and also depends on the areas. So I cannot say how much electricity we can generate, but from small power just to power a sensor, wireless sensor, to something. If you have a huge oven in industry or a chimney, then we can, in principle, put our harvester on this surface to generate electricity for many, many years.
Yeah. Are there any universities? Are there any books that are absolutely ahead of this?
There are many. There are many universities. So thermoelectrics as a fundamental phenomenon is still not quite clear. This is the phenomenon behind it, how it happens, and how to improve this is still a very hot topic in academia.
Mm-hmm.
There are many universities. We have the international and European, is also Asian version of the conferences on only on thermoelectrics. So there's a lot of activities in research areas. There were tons of books if people are interested.
Okay, and on the material side, has it settled with the zinc antimony? What was it, manganese?
Zinc and timonite. It's
Zinc
one of
and
the material
timonite.
that we have been working and we're still working with.
Yeah. Is that the material for the future, or do you think other materials will appear with better thermoelectric properties?
I said there's no best material. There's no perfect material. There's only suitable materials. For some applications, zinc and timonite is a good material for us because we have know-how and we know how to produce it in a scalable and affordable way. But there are also new materials coming out every day, every year. We will keep our eyes open. And I said, by having a material is just the starting point. You need to put the material into a component and then put a component into a system and integrate the system into a product and install the product into the application before you really see the benefits. So it's a very, very long value chain.
Yeah. Thank you, Hao. I have learned something new today. So even though you were teaching me while I was sleeping in the car, not every, maybe it didn't settle at that time, but you have leveled up my knowledge on thermoelectrics. So I would like to thank you very much and thank you for joining the podcast.
Thank you for having me. It's absolutely my pleasure, Peter.
I hope that a lot of people will see it and contact you if they want to learn more.
That would be great.
Yeah. So thank you again.
Thank you, Peter. Take care. Bye.